Okay, thank you. Okay, guys. Let me just start by saying, please be quiet, guys. Don't start side conversations. If you have a question, point it at me, ask it. Let's everybody learn something from. Do not be the cause of delay in everybody. All right. Let me get back to the topic of deadlocks. Anybody knows what a deadlock is? Anybody can remember what conditions are required for a deadlock to happen? Name one condition.
That a resource is not shared.
The resources not shareable. That's mutual exclusive resources.
Non-preemptive system.
And non-preemptive. We can, no. Okay, who can tell me what does non-preemptive mean? What does non-preemptive system mean to a system? Anybody there? Guy near the window, yeah? Yeah? You know what non-preemptive means? Please, yeah. You. I have somebody in the back there. Okay, anybody? Any hands up? Non-preemptive. You know what non-preemptive means? Yeah? At this stage, you should know, I think. Yeah?
The process cannot be interrupted or stopped.
And you think it's already stopped. Okay? Yeah, what's non-preemptive? You have your hands up or yeah? What does non What's non-preemptive system? Yeah, a process may be interrupted and we take the resource away from it. So it's taking the resources, the preemptive part, okay? It's taking away something from that process. Sometimes it's already interrupted. The process is asleep, waiting, but it has 2 or 3 resources. Can we take one of them? If we have a preemptive system, yes, we can. If non-preemptive, that means we cannot take a resource from a process until it finishes with it and gives it up voluntarily. That's the second or third condition of a deadlock. So if the resources are mutually exclusive, and if we cannot take away a resource from a process, that's condition number 2. It means non-preemptive. What's the third condition? Guys, you need to know those conditions. You need to know them so fast. Not just that, you need to explain what it means to be non-preemptive. You know what the third condition is? If I say to you, no, hold and wait, or hold and wait, what does it mean? What does hold and wait weight mean? Not really. What's hold and weight? Or weight and hold?
One device has one resource and the other has one resource. They won't hold it until they're doing
Yeah. If a process goes into a waiting state, if a process has a resource and it needs another one, but the other one is not available, I mean, you're going to waiting for that. While holding the other resource. So if a process is allowed to go in a waiting state while holding a resource, if it's allowed to do that, that's the third condition that will bring us much closer to a deadlock. So if resources cannot be shared, and if you have one, we cannot take it from you, and if you are allowed to go to sleep with 2 or 3 resources you hold in them, then the last condition is called a circular wait. So if we have a number of processes, one is waiting on the next in a sequence, but the last one is waiting on the first one, then they form a circle. Then that's it. There's a deadlock. That's the last condition for a deadlock. You need to know those conditions off the top of your head, and you need to be able to explain what each one of them is. So non-preemptive. You remember what non-preemptive means in the system? A system that's non-preemptive. Anybody? You know what non-preemptive is? I think they have some people who are planning on not passing exams this year. Maybe the summer exams, or maybe coming back here next year. Please don't be those people. Stop time. If you leave it to another week or 2, it's going to start piling up. You're not going to have enough time. Start planning your study, how you're going to be studying. Yeah, non-preemptive.
Not touch about the process and take away its resources.
And take away a resource that it's holding, yeah? Okay. What's a quantum? This is from the week before. A quantum.
It's time.
No. What's a quantum?
Time.
The maximum time. It's not the time, it's the maximum time a process is allowed to have a CPU for. Okay, so that's called a quantum. Is it better to have a long quantum or a short quantum? Which one is better? Any idea? It depends, yeah. Okay. What's the problem with long quantum or short quantum? Which one is better? What do you think?
Well, short is going to preferably too long, then it's like finish with the time, so it's the same as,
First come, first served, yeah. So long quantum allows a process to have the CPU for as long as it wants, but that's bad because it's going to delay everybody behind it. And if we have interactive systems, that's not good. That's not good for interactive systems. And what's wrong with a short quantum? Okay, well, let's cut quantum really short. Give CPU to everybody, come back again, give it to them again. What's wrong with that? Short quantum. What's wrong with short quantum? You look like somebody who knows it. You don't want to tell me, right? What's wrong with short quantum? Anybody knows what's wrong with short quantum? Yeah?
The CPU will be idle for most of the time.
The CPU will be idle because every time you want to take CPU from one process, give it to the next one, the CPU doesn't work during the transfer. So if the short quantum, that means you'll be doing a lot of transfers. That means the CPU will not be working for a lot of the time. So CPU utilization goes down. What do I mean by utilization? What's CPU utilization? What does utilization mean? How is it measured?
100% of your capacity of the process. CPU, you should choose 100% because.
Yeah, we should have 100% utilization. But what does the word utilization mean? How is it measured? Any idea? How do we measure utilization of any device? You have an aeroplane, you own an aeroplane, and we say your aeroplane is 100% utilized. What does that mean? capacity of that airplane. If you have 100 seats in the plane, but you only 80 seats are booked and passengers are paying, that's 80% utilization. So the way it's calculated, guys, how much of the resource is used, say in time, to the total time. If you have an hour of CPU time, how much of this hour it was used? Let's say it was used for 50 minutes out of 60 minutes. That's 50 divided by 60. Whatever the percentage is, that makes a percentage. So whether it's a device, an airplane, or a train, or a CPU, or memory, utilization is how much is being used compared to the total amount that could have been used. Let's get back to deadlocks, or process management. Process management, we need to manage processes if we have multiple processes running in a system, or parallel processes. So if we have many processes running, we are able to manage it, but they can cause problems. And these are some of the problems that can be caused. One problem is called the race problem. Anybody heard of what the race problem is? I probably talked about it last week.
I don't think we did.
Okay, we'll do now. Okay, let's talk about the race problem first. That can happen because we have multiple processes running. Think of this. Here's an example that shows you what can go wrong without any errors. There'll be something wrong, but no error is discovered by operating system or by a user. And one of those problems is called the race problem. So imagine this is your bank account at AIB or Bank of Ireland, and you have 2,000 euros. So you're a rich guy. Right, now you have 2 more thousand euros you're going to launch into that account of yours. One is in cash form. There it is, 1,000 euros in cash. You're going to lodge it, you're going to walk into the bank and throw it at the desk and say, right, put this in my account. But also, you have a check. Somebody wrote you a check for 1,000 euros. Maybe the college said, hey, you pay too much fees. Here's 1,000 pounds, we are refunding you. So now you have 1,000, they're going to go into your bank account. Your bank account already has 2,000. So hopefully at the end of the day, you're going to have 4,000 euros. That's what we should have. Right, and you lodged the bank yesterday. You lodged the check at the bank yesterday, but it hasn't been put yet. And today you walked out with the cash. So at the same time, you walk to the cashier. So there's a cashier at the bank sitting there and counting that money you gave them, and they're going to put it in your bank account. When you start writing code, writing programs, this is the way files are updated. Your file is sitting somewhere there on a hard disk. You want to change the value. Somewhere there's a record there that belongs to you that says there are 2,000 euros in your balance. So your program would say, open that file, find that record that belongs to this person, read me the balance. So you send request, read balance, you get back the balance. There's the balance, 2,000 euro. You have the balance, add to it the new value that we're going to add, 1,000. Now B, the new balance is going to be B plus 1,000. So now hopefully the new balance is going to be 2,000. Now write back new balance to the file. Every time you want to update a file, if you're going to update the value that's already in the file, sometimes you just send a new value, but to update your account, your balance, you must read what the existing balance is, send a read request, get the existing balance, add to it the value you want to add, and say write it back. And in your bank account will go the 3,000. That's the way it works. Anytime you need to update any database file that has a value, you want to add something to it or remove something from it or do some calculation and write back the value. You'll need 3 or 4 lines of code. obviously you open the file, you find the record, and you say, read me that record, look at the balance, add value to it in memory, and say, write it back to the file. So that's the way it normally works, and there's no problem most of the time. Now, imagine you walked into the bank with the cash, you just handed it into the cashier, while at the back office, there's another employee at the office is looking at that check of yours at the same time. They're both going to write to the file almost at the same time. So let's say the file is sitting there somewhere. There it is. So this guy sends a request and say, get me the balance, read the balance. This guy here, you walked in, gave him the money, you opened their account and said, okay, read me the balance at the same time. One of them is going to be read 1,000 or a millionth of a second before the other one. So this guy is going to get a response. The balance now is 2,000. Immediately after this guy is going to say, the new balance is 2,000. This guy says, okay, I'm going to add 1,000 to it, hit enter, and write the new balance. That means make the balance now 3,000. This guy also receives that 2,000, adds the 1,000 from a check, and say, write the new balance. That's 2,000 plus 1,000, write 3,000. Whichever one of them, this guy writes first, the balance, see at this point the balance is still 2,000, this point of time. Now, this guy writes it, it's 3,000. This guy says, no, write the balance 3,000. See, the command comes in, write 3,000. So this guy writes 3,000, this guy overwrites the 3,000. You end up with 3,000 in your account, which is wrong. It should be 4,000. Because those two, this 1,000 from here and that 1,000 from there, each one of them got the balance. It's 2,000, add 1,000 to it, write 3,000. This guy did the same thing, get me the balance 2,000. If that guy wasn't working, that's fine. We just got 3,000 from one of them. The next day we get the other 1,000, or an hour later. But when they write at the same time, one of them is going to read first, then the other one is going to read. You're not allowed to read simultaneously. If two users reach for the same file, for the same record at the same time, there's going to be a problem. The system will not allow it. The operating system will say, okay, 1,000,000th of a second, I'll get you that. So read the first one, read the second one. That guy adds the 1,000 to the balance, and this guy adds the 1,000. This guy say, write it now. So one of them writes it, and then the other one overwrites it. And that's where they started finding these errors. And no error comes up because nobody done something wrong, anything wrong. It's just the way things are synchronized, timing. Because we are allowed to use the same file almost simultaneously. So this problem is called the race problem. It's like race to update the record. Whoever updates it last is the final result. And that's not necessarily the right result. So they made a simple solution. This many years ago, 30 or 40 years ago, they said, okay guys, anybody who wants to work on a file, let's have something like a lock on that file. If you open a file, if you ask any operating system to open a file, tell the operating system, I'm going to be modifying that file. The operating system will put a lock on it for you. So this is locked by you. Let's say this is user A, this is user B. Whoever gets in there, let's follow the same sequence again. Yeah. This user A, user B, the balance now is 2,000. This guy wants to add 1,000, and this guy wants to add 1,000. So they start running, and they'll do it simultaneously. And the file is sitting here. Here's the database. Here's your record in the file, and theirs has 2,000. Now they start running. They both receive this guy receives the check of 1,000, this guy receives the cash of 1,000, and say, okay, let's run. So this guy says, read me the balance. So it reads the balance and gets 1,000. Almost at the same time, or maybe slightly before it, this guy says, oh, read me the balance, and it will get the balance. I'm assuming let's say the file is in the back, so this guy writes this way and gets back. So just so they won't cross over here. So this guy also says read the balance, as this one says read the balance, and we'll get back, here's the new balance equals 1 or 2,000. So both of them, both of these guys got the new balance, 2,000. But with the new locking system, if this sends a request and say read me the file, I'm going to modify it, then it will put a lock on it. It's locked by user B. So now it's locked for user B. Now the request immediately after that comes from A. We say, A, sorry, the file is locked. You cannot read it, you cannot look at it, you cannot modify it. So what do? It's not available. You go on a wait, in a queue. So A is waiting. We don't even answer it. It's only a few millionths of a second, maybe a couple of thousandths of a second. Because this guy reads it, this guy is waiting, cannot go any further. We didn't even send it this balance. So this guy is waiting for the read to come back. It doesn't come back because there is a lock on the file. So when we send the balance to B, and B adds 1,000 to it, so new balance equals the old balance plus 1,000, which equals 2,000. Write, and issues the command, write the new B. So it writes, sorry, that was 2,000. What's the balance? 2,000 plus 1,000 is 3,000. So now it becomes 3,000. Are you finished? Yeah, you want to close the file? Remove the lock. The lock is removed. So now there's somebody waiting on the file. Now we'll open the file now for A and put a lock on it for A. So now A comes into the file. And they wanted to read. Now we send them the new balance. The new balance is 3,000. As you can see now, we got a different balance now for A. After this was updated to 3,000. Now, A gets the balance 3,000. We say B, the new balance equals the old balance plus 1,000. That means B now equals 4,000. Write B to the file. So it writes, overwrites the 3,000, becomes 4,000, and close the file. That means remove the lock. So with this simple technique, we just put, and this lock can be just a bit. We don't mean a lot. Just 1 bit, 1 or 0. If it's 0, the file is open. Anybody can use it. If somebody starts using the file, we put the lock 1. We say 1. If it's 1, that means, sorry, somebody is using the file. You cannot, you have to wait. We put you a wait. So this is the locking mechanism. This is how they were able to solve the race problem. Make sure you understand what the race problem is, how it happens, or how it's solved. You might be asked a question. You know, what mechanism is used to solve the problem, the race problem? And that's locking, using the concept of a lock. It's not a real lock, but it's just a concept of a lock. If any user opens any database file, any file, with the intention of modifying it, all operating systems now do that. They put a lock in it for that user. Another person, maybe 10 more requests come in. They have to wait in a queue. We will not respond to any one of them until this user closes the file and removes the lock. Then we give the file to another user, the next user, and lock it for that user. And that solves the race problem. So that's one problem that started happening from multiple processes working simultaneously using the same resource or the same file in this particular case. There's another problem. It's caused by synchronization. Again, the word synchronization means timing. Your timing is wrong, that means you're not properly synchronized, or two processes are not nicely synchronized. That means they need to adjust. One of them comes first, then wait, or so timing. It's anytime you hear the word sync, means timing is involved. Very important timing to follow, to stick to. Synchronization. Synchronization can cause also, or lack of synchronization can cause many problems. and we will look at it maybe next week. But I'll just tell you briefly now what it's like. Imagine you have storage place, physical storage. And I don't know if there's a machine like this, it's called a forklift. A driver sits here and he can carry big boxes and move them in. Imagine there is a gate here. They don't even, they have like plastic cover on the gate. They just push right through and they place the boxes in there. So here we can store boxes in this storage place. And on the other side, there's also another door. This is where boxes go in, and that's where they're taken out, put on trucks and sent for wherever, for shops or supermarkets or whatever. But this is the storage space we have. What happens here, these guys that drive those forklifts are really good drivers. Good drivers as in, they use one hand for the steering and they're really fast and they move really fast in and out. They can even spin around themselves. They like that kind of style of driving. Unfortunately, in there, there's not a lot of space. And because of these plastic curtains that they have, they just come right through them, push the doors open or the curtains open, and they drop the box in there, come back again out. But there are two forklifts, one on either side. There's another one here. And this guy goes in and only for taking boxes from the store, this one only for putting boxes into the store. But this is forklift A, this is user B. Well, sometimes this guy, A, goes in and there's no room in the storage. It's all full to the rim. He goes in, immediately crashes into one of the boxes. He cannot put, so we said, listen, if this is absolutely full, we put a little light here, green light, or is this full or empty, basically, full or empty. Or we can put 1 and a 0, 1 for full, 0 for empty. If you see 0, we tell them, or green light, you can go in, it's not full, there's place in there. If you see the red light, or 1, that means there's the place full, wait. It's like a lock, controlling lock. It's just, we tell it, listen, the place is absolutely full. You can't put any more, so there's no point of driving. Wait here. On the other hand, the other guy that wants to go in and take boxes from the storage, if the box is full or has 1 or 2 at least, okay, they can go in. If it's absolutely empty, there's no need to go. What they used to do is that they drive in, they find it empty, they come back again. 2 minutes later, they drive in, they find it empty, they come out. Say, no, don't even go. You don't have to go. If it's empty, you must not go. So we put another light or, indicator here, green or red. Green means go in. There are few boxes in there, at least 1. Go and bring it. If it's empty, we put red, or we can put 0 and 1. So if you see 1, you can go in, 0, you cannot go in, and so on. So we had control for this guy and this guy. And even sometimes if there are 3 or 4 here, that means this guy can go in, and this guy has a box, and there are only 3 or 4, they can go in. That's another problem. If they both go in, they crash. They're not great, they're great drivers, but they're not safe drivers. So we don't want the 2 of them to be in there either. That's another thing. So in there, that's a mutually exclusive place. That means, what does mutually exclusive? That means it's not shareable. Only one user at a time. Mutually exclusive means only one user at a time. Don't forget, at a time. Not one user, absolutely, only the same person can go in. No, that person or that person, as long as it's only one person going in. Now, only one person can go in there. That's what the word mutually exclusive means. So that's another control, another little control here beside. So we have 2 controls. We have another little light here, red or green. This is called the mutually exclusive warning. red and green. What does this mean? If that guy goes in here, he'll switch this light here red. That means don't go in. Maybe puts it to 1. That means I am in, I am going in. So this guy has to wait until this guy leaves. When does this guy leave? We don't want him to drive in to see if that guy is left or not. No, they say just go to sleep. Sit there outside until this guy leaves. And when that guy leaves, it will turn that light into green. So it will switch this light off or turn it into green. And similarly, if this place is empty now, that means the light is green, and this goes in here, that guy must not drive in from the other side, because this place is mutually exclusive. That means when this guy goes in, this indicator, in fact, it's the same indicator. They both can see the indicator over maybe the roof of the storage. So if it's green, this guy can go in, or this guy can go in. But you must turn it into red for the others, nobody else to come in. So we look at those two mechanisms. They control the timing, the synchronization, when these two processes can work together without major damage, without any damage. This is something like the critical section that train companies used to have. Remember, in trains, if a train is coming in from this direction and the train network shares this part is a shareable part. We call it critical section or critical region. I'll call it region, okay. But both names are used, critical section or critical region, especially when we code. So if this train comes in from this side and this train is coming in from this side and they both enter into the critical region, they're gonna crash. So we want to make sure, and that used to happen to train companies, and it still happens. Every now and again you hear about two trains crashing. Why? They met in a critical section of the track. Why? What control were used? So they used something. We call it a semaphore. And a semaphore is a very simple signal. Let's see how it works. The semaphore is like, again, like a traffic light. It has two positions, green or red. And let's say, or 1 and 0. We can still use 1 and 0, but imagine it's green and red. So we have a light, and now it's green. What does green mean? It means there's nobody in there. So that this train comes in, looks at the distance and can see the green light. Say, great, there's nobody in that. I don't even have to stop. They might have to slow down. And there's a lever here. Maybe it's even automated. But the driver, while passing by that lever, hits the lever and turns this green into red. That means I am going in there. I don't want anybody else. So the light goes red while this guy is in there. Now, if another train approaches, they can see the red light. They must stop here. This is how the semaphore works. When this guy leaves the critical section and heads off, just leaves this part, he passes by the lever and he hits it and changes the red into green. The green light is back on. This guy sees that green light. Sometimes it might take 10 seconds, half a minute, 5 minutes, who knows? Depends on the length and the speed of that train. This guy doesn't have to keep looking at the light. Sometimes they take their eyes off and say, okay, the light is red, let me go and put the kettle on. And they make a cup of coffee. When this guy turns the green light off, maybe someone else will come in, see it green, switch it on and go in. So this guy might miss its turn. And if they keep missing their turn, we call it starvation. We don't call it a deadlock. Or just missed your turn a few times, you're delayed for a long time. But forget about the details. Let's just see how it basically works. So this guy comes in, if it's green, hit the lever, turn it red and go in, knowing quite relaxed that there's nobody else in the critical section. And anybody approaching the critical section, they'll see the red light until this guy leaves, hits the lever, turn it into green. Now this guy that's waiting, say, okay, now it's gone red. Sorry, it was red, it turned into green. This guy can see the green light. You say, okay, let me hit the switch or the lever and turns this into red, and now this one can move. So any other train approaching, they'll see the red light and they'll have to wait. That's how semaphore works. Sometimes they still crash. That's how what trains use in those, wherever there are train stations. Okay, so let's see just one little problem with this. We'll talk about other problems like missing a turn if you don't keep your eyes on the thing. And you're not supposed to keep your eyes. You're supposed to go to sleep for a little while, take your eyes off it for a few minutes, and look again. But when you take your eyes away from it, maybe that guy has left, turned it green, and another approaching train will come and pick it up before you look again. But anyway, let's look at the dangerous part of it. This guy comes in, let's start again, finds the light green, hits the lever and say, okay, turn it red. No. Let's start again. This guy comes in and looks at the light, it's green. Meaning, nobody's in the critical section. Also, at the same time, this guy approaching and looks and can see the light green. Both looked at the same time, and the light is green at the same time. The protocol says when you see the light green, then you hit the switch, so you'll book it. So they both hit the switches or the levers at the same time. And they look and they see the light gone red. Each one, user A or B, they've been looking at the light, it's green, they hit the lever, it's gone red. They don't know that someone else did exactly the same thing at exactly the same time. And each one of them thinks it's green for me now, it's red for the others. And they both drive in, hoping or thinking there's nobody on the track, when they both are on the track and they end up crashing. So if it happens exactly at the same time, it can be a problem. And they solve that problem, they solve that issue. That checking the light and hitting the lever, they made it just one instance of time. It cannot be duplicated. But we'll look at that later on when we do critical sections. That's on train stations, they protect the critical region. But on computer programming, where do we use it? And in computer programming, we've talked about memory. If you have a huge amount of memory or some amount of memory, and you want to run programs, your code is actually put in memory. Let's say job number 1 or program 1 takes so much space in your memory, whether it's continuous or non-continuous, it takes a certain amount of space. Another program number 2, program number 3, you might be able to run 5 programs or 6 programs. Even sometimes, and notice something, that programs are not allowed to communicate together inside memory. This program cannot access the memory of this program. Let's say the variable x here equals 10. This guy can never look at that variable that belongs to another program because of the protection that operating systems impose on processes. You cannot go to another area and check what values they have. If this guy has an array here in its memory, this guy cannot reach it, cannot put something in it, cannot modify it, cannot read it. So really, processes cannot communicate while they are running, while they are executing. We know that. The only way they can communicate is outside memory. For example, a file. Imagine this process opens a file and writes some information into it, 4, 7, 8. Now another one closes the file. Now another process can open this file and read that information. That's possible, but that's so slow. Imagine opening a file, a hard disk has to start spinning. Maybe it's spinning already, but still slow. It might take 2 seconds. 2 seconds in memory time, hey, we can transfer 2 million bits if we could do it inside main memory. But we couldn't. We had to use a mechanical device, which is a very primitive device, such as a hard disk. It might take a second or two, when we could have done it in a millionth of a second or two. So that's the only way processors communicate, guys. Outside memory, not inside memory. Which is okay most of the time if maybe a company has an employee, maybe you're doing the staff database, a new employee comes in, you enter it, you write to the file, you close it. The next day someone else open another file, give me the list of employees, they'll be able to see that employee. That's how information is exchanged between different processes. But sometimes that's not good. Like, for example, in a factory. Remember a factory, one process does something, let's say you're manufacturing a car. You get in the frame, you maybe bolt it together and move it forward. Here they put on the wheels onto it. Now you move it forward, you put the glass onto it and put the engine onto it. So every stage, every process happens as the car is moving or the item is moving in a chain. And every process will do something. There are programming techniques that actually use the same thing. We have a program that generates a list of numbers, give it to the next program, we'll sort them out, give it to the next program, we'll, I don't know, pick something. But they cannot do it in main memory. But they came up with a new idea. They came up with something called threading. Programming using threads. Have you heard of it yet? You'll be using it. Maybe next year, you'll be writing threads. What's the point? What's the idea of a thread? The thread is simple. Imagine if you have, again, the same memory, and you have a program here. You have the code of a program. You have the memory, the variables, that's X, Y equals whatever, and then the code. That's what you get in memory. The code part, the data part, they call it. That's where you get your variables as well. And there's another part called the stack part, but don't worry about that. Now, they found something that if you create a thread, that means you make another copy of this program. Let's say you want two programs to do two things. One generate numbers and give them to the second program that sorts them. You can write one program and you call this the one that generates the problem, the numbers, and this is the one that sorts them. Write them in one program, not two separate programs. And at the start there, when the program starts running, you can say thread. That means create me a thread. Thread is a copy of this program. Give me another copy of it. The advantage of it, it's going to be, imagine if you have another copy of it there. But in fact, it's the same copy. We're not really creating a copy. We're using the same code. But we're creating another process that runs on the same code. This is like, imagine if in your kitchen you have a recipe stuck on the wall. That's the code to make a cake or a trifle or whatever it is. You walk in there and you start working in it. That's chef number one. You start executing the instructions. You want line 1, 2, 3, 4, you're at line 17. You're making whatever the meal is. Another person walks in and they start executing the same thing, but they make their own meal. They're both making exactly the same meal. But now I have another user that started at line 1. So we are executing the same code, but there are two of us working. One is at line 1, 2, or 3. That's really at the start, still holding the eggs and breaking the eggs. While the other one is at line 17, almost, whatever, doing the last part of the cake before putting it in the oven. This is exactly the same as this. We have two processes running, but they are using exactly the same code. That's the idea of threading. That's why threading is so efficient, that you can make multiple copies of the same program, and each copy will be a separate user, separate process running, but they're all running on the same code. That's very good for memory. You don't have to duplicate, you don't have to have more code for another process in memory. That's the biggest, one of the biggest advantages of threading. You're sharing the same code. What's even better than that, the bigger advantage of threading or using threads, is that they all share the same memory, including the variables. Which means if this guy, the first program, now what you can do is say, okay, if you're, the only difference between those different copies of processes is their ID. That's the only thing. You are process number 1 and you are process number 2. You're running exactly the same code. So inside you can say, well, if you are process number 1, do this, and if you are number 2, do this. So it's like each process went to the part it wants to do. What's good about this? If this guy says x equals 7, this guy can see it, because they all share the same variables as well as memory, the rest of memory, including the variables, which means they can talk together at the speed of light inside memory. That's the advantage of threading. You can take 2 separate programs, put them into one, and run them there, and issue. And the command in C is fork. I don't know what other, each language has a command. You issue it, it gives you another process on the code. It's like another chef walks in through the door. Every time you say fork, that means give me like a separate path in the same code, a separate process. So you can have 4, 5, 7 processes running on the same code. And they all can access the same code. So if there is an array, this guy can start putting numbers in this array, and this guy can start reading those numbers and doing whatever they want to do with them. So that's really thread processing, or coding using threads. It's a fantastic kind of innovation, and it's worked well. It saves memory, and it allows processes to talk together inside. So now, just imagine each one of them is running. Like this one, process number 1 is running, and of course on top of it is running process 2, but I'm just going to put it beside it. And they're running exactly the same code. Remember, it's only 1 copy. I'm just putting 2 to make it easier to imagine it. So this guy is running code, maybe line 1, 2, 3. This guy is running code number, line number 700, 800, doesn't matter. And then this guy can be sent back up in a loop, and they can be executing exactly the same line. It doesn't matter. But there are certain parts of code, this part here, if they both execute it at the same time, there's going to be a problem. And that's what we call in coding the critical section, or the critical region of a program. So there's no problem, generally, there's no problem running the same code many times, many copies of it, and many, like 3 or 4 processes running exactly the same code. But there are certain lines of code, they found that, if we run the same code many times, this process does, and this process does the same line, we're going to have a problem. Whether it's a physical problem, like there's a collapse, the program stops, or we get an error like in the race problem. Remember, with the race problem we looked at earlier on, you get an error in the data, but there's no physical error. You don't get an error, operating system stopped this program, they committed an error. They did not commit an error. But with the lock, we solve that problem that happens here. Again, certain parts of the code should not run. When even in the same program, sometimes you might find 2 parts of that code that's critical section. Here's a critical section, and here's a critical section. So how did they solve this critical section? This critical section, imagine, look at an aeroplane. Imagine you're flying an aeroplane. Is the aeroplane shareable or is it non-shareable? It's shareable. 100 people are flying on the same plane, but inside that plane, maybe there's the toilets. If you decide to go to the toilets, that part, the toilet, is mutually exclusive. What does mutually exclusive mean? Anybody knows what the word mutually exclusive, what does it mean? Only one user can use it, right? Not exactly. Not at a time, thank you. So mutually exclusive, that means only one user at a time. When you finish, another user can use it. So don't just say one user only. That's wrong. Many users can use it, but not at the same time, only one at a time. So the toilet is something like that. So this is exactly what we are looking here at, this critical code or the critical region. The program is like the aeroplane. Everybody, lots is shareable, but this part here is not shareable. It's mutually exclusive, and we need to protect it. And how do we protect it? We protect it with a semaphore, like a little signal, a little variable, just like we did with the train. You can have a variable and you say, okay, X is our protection here. X is 0, that means there's nobody there. If you reach this point, check it, is X 0? Yes, it is. Well, turn it into 1 and go in there. So the next program that comes in after you, if they check it, if it's 1, then they have to wait. This is in its simplest form. You have one variable. You either turn it 0 or 1. 0. This is exactly what they have on the toilet doors in airplanes. That's how they solve the problems. In the old days, they had a toilet, everybody opens the door and closes it. No, they put a little sign on the door that says occupied and free. It's 0 and 1, or 1 and 0. And there's a little latch. So and this is the protocol. You go in, you look at that sign. Is it free? No, it's not. But then you have to wait. Exactly that's what programs do here. Is this part free? No, it's not. They see 1. That means there's some 1 in there. When that person comes out, they open that latch. Guess what happens? That's turning this 1 into a 0. That means now that place is free. You go in, first thing you turn that thing to 1 and go in. So you go in and you make sure that's exclusively yours until you finish. So the problem is a bit more than that, but this is the general idea. If you understand this idea, you have no problem going through the critical section when we get to it tomorrow or the next week. So that's because we're using threads, and with threads we can share the same programs in same memories, one copy of the program, but multiple processes will be running the same one, and they can run most of the code without any problem. But if they execute some of the lines of code, which we call critical section, they need to be protected by you. And how do you protect them? You put a semaphore before them, or that signal before them, and you have some code that if it's 0, you can go in, but make sure you turn it to 1. If you forget how it works, think of the toilet and the airplane. It's exactly the same idea. So that's threading. So which is better, running 10 threads or 10 processes? Anybody? Is it better to run 10 separate programs or run 10 processes but threads, 10 threads? Run one process and fork it, get multiple copies of it. Which one is better? Any idea?
The threads.
Why?
Because you run sequential the programs inside of the process, no?
But even with the processes, they're unsequential maybe. They don't have to be sequential. Sometimes they jump to different processes and different functions. Okay, well, threading is better, but anybody can give me a reason why? What's the advantage of threads, yeah?
Saves memory.
It saves memory. If you run 10 programs as threads, you only have space of 1 program. If you run them as 10 separate programs, you need 10 amounts of spaces in memory. So it saves you a lot of memory. It's the most efficient way of using memory. But what's even more important than that? What's the other advantage of threads?
It's faster.
Why are they faster? Faster in what way? CPU runs at the same speed, so why is it faster?
Yeah, but it does not need to interrupt as often to like switch from one program to another because it's separating threads.
Yeah, because the processes that are running on these threads can communicate together because they have access to the same memory, to the same variables. I can write a value in X and you can read it immediately. But if they were separate processes, not threads, and we have to write into outside memory, into a file, and then you have to go and read the file, and that's where the slow thing. So we are probably 1,000,000 times faster using threads when we want to exchange information between us, between the threads that are running. It's a lot better. But, of course, it has this problem with the critical section. They found programs have some parts of their code that cannot be executed simultaneously. Some lines are okay. Most lines, they'll have no problem. Even when they're running, remember with the two chefs that walk in there earlier on, I had them, even if they run at the same time, it's okay, they can do. But seemingly here on threading, it's not a good idea. It's okay to run the same lines, but some lines are not to be executed simultaneously, and we need to control them, and we call them the critical region. Okay. Now, finally, what I want to show you is a diagram. Anytime we run a program, we're going to use the following diagrams for another purpose, for detecting a deadlock. A deadlock, guys, happens if we have normally you'd have 40, 50 processes running on a real computer. And remember, if it's only one CPU, only one of them is actually executing at that moment of time. But the rest of them are running, and one is waiting for the CPU, and one has already got the CPU, now it's printing something on a printer, another one that's reading from a hard disk, and they're all doing different jobs. You'll see printers are ticking away, and lights are flashing at hard disks. They're all busy. But there are 3 or 4 of them. And remember, they're all the rest of the process. There's only one that's running. The rest of them are all waiting. Either waiting for something to be read, or waiting for something to be printed, or waiting to store, or waiting for a file to be opened. They're all waiting, but they're not in a deadlock wait. They're all going to get their data quickly, and they get moving. And they go, and then they wait for the CPU, and then they get the CPU, they go out and wait again. But there are 3 or 4 of those processes, they're waiting, but they're never going to get out of that wait. And that's when they're in a deadlock. And this is what happens. Excuse me. This is how a deadlock happens. Give a quick example, and then we move on to how to actually detect it. But imagine if you have 2 resources. You have a file on a hard disk, that's resource number 2, and you have a printer. Oh, sorry. Oh. Sorry, I'm going to start again. You have 2 processes, process number 1, or person number 1, and process number 2. And both of these guys, they need 2 resources. Remember when we talked about the chef? Let's say these 2 guys, they want to cook breakfast. They walk into the kitchen, and the kitchen has lots of tools. They have a frying pan, they have spatula, they have forks, whatever it is. There are lots of tools in the kitchen, but you need this tool and you need this tool, the spatula and the frying pan. So this guy goes and grabs the frying pan. So here's resource number 1, and that's the frying pan. And it's this guy got it. So this frying pan is now with this guy. It's actually a square one. And this guy went for the spatula. So this is resource number 2, which is the spatula, and it's taken by this guy. Now this guy got the frying pan, goes for the spatula, it's not available, so what happens? It's wait. So he goes sleep waiting. I say, okay, this guy who has it will finish, sooner or later will finish. But in fact, this guy who got the spatula, in order to cook their eggs, they need the frying pan. So he goes to grab it, but he can't get it because it's already with the first person. So he ends up waiting. So now, we have two users or two persons waiting. Each one of them has a tool and needs another tool, or a resource and needs another resource that's not available. That second resource is not available. That means they end up waiting. And this guy has this resource and needs the second resource, which is the frying pan. I say, I'll wait till they finish, but they're not going to finish because they wait on one another. So this guy enters into a wait as well. So these two are waiting on one another. And we know they are in a deadlock. That means they'll never come out of this because none of them will finish. Why? Because this guy has the frying pan and needs the spatula. Will never cook the eggs without a spatula. So he's waiting. And the spatula is with this guy who needs the frying pan before they can continue. So he goes to sleep waiting for the frying pan, thinking this guy will finish with it, but this guy will never finish because it doesn't have everything it needs. It doesn't have all the resources. And that's what we call a deadlock. So a deadlock really materializes from a situation where four conditions happen. First, these two resources that we have are mutually exclusive. So that's condition number one. If the resources we have cannot be shared, that's your first step into a deadlock. What's the second step into a deadlock? If it's non-preemptive. That means we cannot take the frying pan from that guy and give it to this one and say, go and finish, and return it to us. If we cannot take it away from a user, then that's called non-preemptive. And in most of our systems, they're non-preemptive. Most of the resources. A printer is definitely the best example of non-preemptive. You can't start printing half a page and then we take it from you and give it to someone else and say you can start writing your report. And on the page you find a bit from the last user written on the page and a bit from the second user. That doesn't work. So that's why we say it's non-preemptive. Wait till they're finished. Right? Okay, so non-preemptive, that means we cannot take the resource from you until you're finished with it. So that's the second condition, and this is the case, seems to be the case with our two friends here. We cannot take the frying pan from the one who has it, or we cannot take the spatula from person number two and give it to one to finish. Third condition. What's the third condition? Yeah, okay. So if this guy got the spatula and went for the frying pan and couldn't get it because it's not available, it would be nice if they say, okay, I'll put the spatula back until the frying pan is, that's called, I don't know what's called, it's called releasing the resource. But what happens? He ends up waiting while holding the resource, and that's called hold and wait. That's condition number 3. We allow in our system a hold and wait. If we allow those 3 conditions, if our resources are mutually exclusive, that means 2 people can't use the same spatula. It can only be used by one person until they release it. And if we cannot take a resource from anyone, and if we allow a process that has one resource, and it needs another one. If the other one is not available, we allow it to go in a waiting state while holding the resource it has, and we cannot take it away from it. That's called non-preemptive, or hold and wait. If those 3 conditions happen, it's just a matter of time before we get the deadlock. And when do we get it? When we get this, what's known as circular wait. And what's a circular wait? Starting at any point here, process number 1, if we follow the arrow, this one is pointing at the resource it wants, but it cannot have. Why? Because it's with another one, so we're moving. It's with the arrows. This is held by process 2. And why doesn't process number 2 run? Because it needs that resource. If we follow it, why not? Why it can't have this resource? Because this resource is with this process. If we follow these arrows, we return to the same point. Doesn't matter what point we start at. If we go back to the same point, that means there's circular wait. And that's the final straw kind of thing. That's the final and last condition. It's called circular wait. If we have a circular wait, normally a wait could be just sequential. One is waiting on this, wants this resource, but this resource with another process that wants another resource, but this resource with another process, but who wants another resource, but this resource with another process. Eventually, this process needs nothing else, or it has other resources. It will finish, it will release this one, this will take it, and then this one will finish, release this resource, so this resource can be given to this one. So as long as they are in sequence, there's no deadlock. When does the deadlock happen? When we have a circle, when we can go back to the same point, and that's called circular wait. So if we have the circular wait, then we have a deadlock. So for a deadlock to happen, there are 4 conditions. All of them must be in the system, and condition 1, and 2, and 3, not or. All 4 of them, and. So when the 4 of them are available, then there will be a deadlock. And they will never come out of the deadlock on their own. Doesn't matter how long they wait. There has to be an outside interference. Usually by us, we say, okay, let's terminate this process. And when you terminate it, the resources become available, the other one can get them. Sorry, what's your question?
There's 6 minutes left for attendance.
Okay, thank you.
Same.
Yeah, same, okay. So you know what are the 4, name one condition required out of the 4 conditions required for a deadlock. One condition required for a deadlock, name one. Mutually exclusive. Name another one. Any guy, any one of you, go on. Second condition required for a deadlock, go on, let me hear you guys. The guy beside the window. No? Okay, next to the... Anybody? Right, I'll jump at you. Second condition for a deadlock. Non-preemptive. If our system is non-preemptive, and then you need to know what these conditions mean. So you might be asked in an exam, what does non-preemptive system mean? Which means we cannot interrupt a process and take the resource from it without it's given it up by itself. Okay, what's the third condition?
The third condition is hold the waiting.
Hold and wait. If we allow a process to hold a resource, and that needs another resource but it's not available, so it has to go into wait. If we allow it to go into wait while holding a resource, that's what we mean by hold and wait. And we cannot take it away from it. That means it's non-preemptive. And then finally we get, yeah?
The hold waiting is the same circular waiting, because the next class you explain like circular waiting. There's an eternal process you never end. It's the same for the waiting.
This is once. This is just wait once. You're allowed to, for example, you need 4 resources, but you get the first one, you will go for the second one, it's not available. You have to wait. You wait while holding the first one. When the second one becomes available, they'll wake you up. The operator says, here's your second resource. You might say, I need a third one. Then you go for the third one and see if it's available. You might end up having to wait for each resource. But you're allowed to hold the resources that you have. If the system says, no, don't hold the resources, that means we're not going to have a deadlock. Because if you have a resource and someone else needs it, you're waiting or asleep. I'll take it from you, give it to them, let them finish and return it to you. But we do not do that. Okay, let's have a quick... All right, guys, let's finish this. So Thank you. Give him a little elbow. There are three symbols that you need to learn to draw a diagram. And you could be given statements in English that say, okay, process number 1 has resource 1. How do you draw that? Process is drawn as a circle, always. This is the symbol used. This is the resource allocation diagram. So this, and you draw the circle and you write, whichever they told you, it's process number 1. So a process is always a circle, a square or a rectangle is a resource. And then there's an arrow, either going from the tail to the end, from a process to a resource, or from a it starts at a resource and it's heading towards a process. You can consider for now just a process like a person. And a person is pointing at something, that means the person says, I want that thing. There are two words used. If the person, the P, is pointing at a resource, it means it's requesting. We use the word request or requests. So if this process 1, if we are told process number 1 is requesting resource number 2, that means it's requesting. That's the way you read it. You always, when you read it, you start at the tail of the arrow, you go towards the direction of the arrow, the head of the arrow. So you're starting here. This is the way you should read it, guys. Aisha, are you listening to me? You say process 1 is requesting or requests resource 2. That's the way it's read. You always start at the end of the arrow. If I tell you process number 1 has resource 1 allocated to it, this is the way it's drawn. And this is the way it's read. We say resource 1, you always start at the end of the tail of the arrow. You say resource 1 is allocated. Anytime you start with resource, you always say allocated to process 1. It's like we say, right, you point at that seat, can I have that seat? And we say, yeah, you can have it. I mean, it's allocated to you. So we can reverse the direction of the arrow. So now, this process is requesting that resource. If the system gives it the resource, we'll draw the arrow in the opposite direction. Well, that means the resource is allocated to the process. But now, this is the situation. Process 1 is requesting resource 2, and process 1, actually, resource 1 is allocated to process 1. All right, and so on. And we can make it even more complicated, and then we can have process number 2. The process number 2 maybe has that resource. So how would you read this? How would you read this relationship between this resource and process? Sorry, this is process number 2, and that's resource number 2. Can you read this statement for me? This relationship between resource 2 and process 2? How would you say? Yeah?
Resource 2 is allocated to
Allocated. Remember, always, if you are starting with resource, it's allocated to the process. If you are starting, say in this case here, from a process, it's pointing a resource. It's like you pointing a resource, say, I want that resource. So process 1 is requesting resource 2, but resource 2 is allocated to process 2. So if you get the statement in English, you translate it into a diagram. If you get the diagram, you can read it in English. And you always, to read, you always start at the end, the tail of the arrow. If it's a resource, then the next word is going to be allocated to that process. We don't have two resources pointing at one another. or two processes pointing to one another. So the relationship is always pointing from a process to a resource or from a resource to a process. And it's either, if it's from the process, it's requesting that resource, and if it's from the resource, it's allocated to this process. There's one other symbol that's not shown here, and this is another multiple instances of the same resource. Sometimes you get a rectangle with maybe 2 or 3 dots in it. What does that mean? This is resource 3. That means we have resource 3, we have 3 items of resource 3. It's like, for example, we have 3 printers, and they are identical to the point that it doesn't matter which one you get allocated, it will do. If there's a difference, then they are not the same instances of the same resource. All right, so that's also a resource, but we have 3 printers here. One of them, for example, may be allocated to process 1. So this one, you'll start at the actual instance itself. This instance is allocated to process 1. So we say allocated. And really the way to read it is say one instance of resource 3 is allocated to process 1. And maybe this process is requesting some instance, so it's not been allocated one of them yet. And so on. So we can have another process just for fun. And it actually needs that resource, and it needs that resource. Okay, and we can have as complicated, diagrams as we can. This can happen in real life in a computer system where this could be printers, that could be a file, that resource can be a hard disk, whatever it is. And different processes need these. And these resources are not shareable. They are mutually exclusive. Can you tell me what a mutually exclusive resource is, please? Yeah? Put your hand up with the black shirt, yeah.
Mutually exclusive resource is that only one process at a time can use it.
Almost there. The person next to him, what's a mutually exclusive resource?
Honestly, I thought the same.
Exactly, at a time. Only one user can use it at a time, at one time. Is that what you said? Yeah. That's how you'd get the full mark for that last word. If you miss that last word, you wouldn't get. Be careful. Right, and then shareable resource. What's a shareable resource?
We can use, for example, to have multiple processes, and we can share
So-
variables or information between them.
So one resource can be used by multiple users. What's a shareable resource?
It is when you can use one device and share this device. You can share
Between
this
multiple users.
multiple users, yeah. Like a display load.
What? No, it's wrong. What's a shareable resource?
Resource that can be used by multiple users at a time.
At the same time. Don't forget the word at the same time. A printer can be used by 1,000 users, but not at the same time. Be careful. All right. Now, how do we know whether there is a deadlock in a system or not? Maybe it's easier to, okay. I'm going to have a quick system drawn here. 1, 2, 3, for example, and 1, 2, 3 processes. This one has this one, and it needs this one. That one has this one, and it needs that one, and this one, and that one has this resource allocated to it. Right, let's look at this system. This is process 1, process 2, process 3, resource 1, resource 2, resource 3. Whatever the resources are, they could be files, they could be hard disks, printers. Now, if you're asked, is there a deadlock in this system? Now, once we managed to draw it, you could have been given those relationships in text, but if you're given a diagram, if you're given a text, draw them first. If you're given the diagram, great. Right. Now, if a process has all the resources it needs, just keep this in mind. If you need a printer and a file, you need to read information from a file, send it to a printer. You have the file and the printer, then you have everything you need, you're going to finish. Sooner or later. It might take you a bit of time, but you will finish. And when you finish, you will release the printer and the file, and we can give them to someone else. We can delete those links that you had. You no longer have them. If we can remove all these links, then that means there is no deadline. We look in the future. Even though it's going to take a minute to finish, well, let's assume it's finished. If you have everything you need, then you're going to finish. For example, you're going to cook an omelette. You need the eggs, you need the frying pan, and you need the spatula. You have them. Then start. We know you'll finish. You might finish 5 minutes. We'll assume you've finished, right? And we go in the future and say, this guy is finished. Only if you have everything. Because you can only finish if you have all the resources you need. So, if we can finish each one of these and remove all these links, that means there is no link. If we cannot finish them, then we'll find a circular weight. And we can follow the circular weight, and we know who is being deadlocked. So let's look at this. How do we go about this? You can go with each process. Start with process 1, 2, 3. There could be 5, 6 processes. You go them from 1 till the end and come back again until they finish. Or you can go straight and look directly. Look for any process that has all the resources it needs. If it has all the resources it needs, jump on that one. Say, okay, this one has everything. It's going to finish. Let's assume it's finished now. And you move the links. So looking at these, I'm going to look very quickly. This is what I do. Does process 1 has everything it needs? Are all the resources pointing at it? No. There are 2 links. That means it needs 2 resources. 1, it has it. See, if you read this, resource 1 is allocated to process 1. That means it has this resource. This one, it's pointing away from it. Does it have it? No, it means it's requesting. I want that. See, if it's pointing at resource 3, that means it's requesting. That means it doesn't have resource 3. That means, is it free? If that resource is free, let's give it to it. Is it free? No, it's not. It belongs to another process. That means leave process 1. Let's look at process 2. Does it have everything it needs? It needs 3 resources. One of them is pointing at it. It only has 1, and it needs the other 2. Are the other 2 available? Can we allocate the other 2? No, this one we cannot allocate it to process 2 because it's already with someone else, with process 3. Can we give it this one, R1? No, we cannot because resource 1 is allocated to process 1. And this is the logical. Then it cannot finish. Leave it. Go to the next one. Process 3, does it have everything it needs? It only needs 1 item, and it has it. It's pointing at it. How do we know it has it? Because the arrow is pointing from the resource to the process. That means resource 3 is allocated to process 3. That means it has it. It only needs 1 item. Maybe a printer prints 1 page and finish. Let's say then if this one is going to finish. Why it's going to finish? Because it has everything it needs. And you almost have to write those words in your answer. You can't just say, okay, process 3 finished. No, you have to tell me why is it finished? Because it has all the resources it needs allocated to it. So process 3 only needs 1 resource and it has it. Then it will finish. It might finish now in a minute or 10 minutes, but we know it will finish. And when it finishes, what happens? It will release that resource. Now that resource becomes free. Now it's up to you and me to allocate it. It's up to the operating system. There are 2 processes asking for it. Which one would you give it to? Let's give it to the one that will finish. Don't give it to another one that needs more resources and end up, nothing happening. So resource 3 is going to be given either to process 2 that's asking for it or process 1. Which would you prefer to give it to? Process 1 or 3? 1, because if we give it to 1, 1 will finish. If we give it to process 2, then it'll do nothing because it still needs another resource that's not available. Okay, so make sure you give it to the correct process. So now we give it to process 1. How do we give it to process 1? by saying resource 3 now is allocated to process 1. That means change the arrow now. Instead pointing this direction, process number 1 was pointing at resource 3, so I need that. No, we don't, okay, now you can have it. It's allocated to process 1. Now we can say, process 1, does it have everything it needs? Yes, it needs 2 resources and it has them, both of them. What does that mean? It means it will finish. Now or in a second or in a minute or in a day, it will finish. Because, why you're certain it will finish? Because it has everything it needs. And remember, we can't take it away from it. It's non-preemptive system, we can't interrupt it. So if it has everything, then it'll start printing or doing whatever it needs to do. And then when it finishes, it will release or relinquish. There are 2 words used in this technique. Okay, so it's either requests, these are the words that you need to learn. Request, allocated, or release. These are 3 words. Request and allocate depending on the direction of the arrow. When it finishes, it will release the link. So now process 1 finished. It's released resource 3. What are we going to do with resource 3? Who wants it? There's only one process that wants it. Give it to it. So process number 2 needs resource 3. Let's allocate it. So now resource 3 is allocated to process 2. What about this one here? This process 1 has finished or released or relinquished resource 1. Now it's available. Who wants it? Only process 2 wants it. Give it to it. So now process number 2 has resource 1, it has resource 2, and it has resource 3. It has everything it needs. Guess what's going to happen to that process? It will finish. And when it finishes, all these links will disappear. Now, we got rid of all the links. That means there is no deadlock in this system. And this is called deadlock detection. You'd know whether there is a deadlock or not. All right, I think I'll give you a couple of diagrams and see if you can figure out whether there is a deadlock or not. Now, the way the sequence we released those, you need that sequence. We first, process number 3 finished, and then process number 1, and then finally process number 2. That's the sequence that happened in this diagram, you know, tracing chart or diagram. So think or remember the sequence of events, the processes that will finish, the sequence. Let me just try and think of an example of where there is a deadlock. Just give me a second. So process 1, 2, 3, 4, 5. We have resource 1, resource 2, and resource 3. No, that's the other way around. Yeah, that's okay. All right, look at this diagram. Let's try and finish those 3. Yeah?
Can a resource be allocated to 2 processes at the same time?
No. Yeah, that's a mistake. Where is it? This one here.
Yes.
I've done that intentionally just to see if you're following me or not. Okay. Let's look at this diagram. Is there a deadlock here or not? Okay, you follow the same protocol. Start with the processes, see which process has everything it needs. and let's finish it. And then from there we go, allocate whatever resources are available. So, can you see any process has everything? Let's start with number one. Number one, it needs only one resource. Does it have it? No, because it's not pointing at it. The process is pointing at the resource, says, I need that resource, I'm requesting. So this is the word request here, it doesn't have it. This one is allocated. The resource is allocated. So process one is requesting resource one, but resource one, unfortunately, is allocated to 2. So this one cannot run. It doesn't have everything. If the resource is free, we allocate it to it and we finish it. But the resource is not free, it's with another process. Can this one finish? No, it needs 2 resources. Right. It has one and it needs this one. Can we allocate it that one? No, because it's with another process. What about this one? Can this finish? None of them can finish. Okay, that's bad planning, right? Let's say this one was actually requesting, sorry. So this resource, number 3, is free. It's free. It's not allocated to any process. And who wants it? Process 2 wants it and process 4 wants it. So we give it to one of the processes. Which one would we give it to? That's process 3 here. Well, if we give it to process 3, it will not finish because it needs another resource that's not available. And same as this one. Okay, this is not a great example, right? But, okay, so we can't release anything here. That's terrible. Okay, okay. I'm gonna change it again, but okay, we can't release anything. Do we have a deadlock? Then we must have a deadlock. Where is the deadlock? The deadlock is any sequence that you can follow and bring you back to the same point. So, this one, from here to there, there's no way of coming back. There's no returning point to P1, so let's start from this P2. P2, if we follow the arrow, go down to R2, it requests R2, but R2 is with process 5, so follow it. So it goes from here to there to there. But process 5 has this resource, but needs that resource, and that resource allocated to that one. So it brought us back to the same point. Then this is a deadlock. And you need to write it down. We started at P2, this is the deadlock. I'll write it here. It's P2, it went to resource 2, and it went to process 5, and finally resource 1, and then P2. So there it is. Process 2, resource 2, process 5, resource 1, and process 2. So brought us back to the same circle. That's a deadlock. And who is deadlocked? Process 2 and process 5 through those 2 resources. And here's the sequence of the deadlock. Are these deadlocked as well? I don't know. Let's see. If we start from here, we go this way, we'll never go back to the same point. That's not a deadlock. That's waiting, but it's not a deadlocked with the rest of them. If we go this way, we'll never go that way because the arrow is pointing in the opposite direction. We can actually allocate one of them. Let's say this resource is free. If we give it to one of these processes, let's say we give it to process 3. Does this generate a deadlock? Okay, let's start here. We go there, follow the arrow down. We'll never go this way. We cannot go that way. That's not a deadlock. That's not a circle. It does not bring us back to the same point because the arrow is in the opposite direction. So we have one deadlock. That's the deadlock there. If we follow the arrows, they bring us to the same point. So in this system, we can say, yeah, there is a deadlock. And the ones who are deadlocked are process 2 and process 5. Let's look at a couple of examples on the slides before we go home. And you try and work out whether there is a deadlock or not in the system. Try to understand it. You learn it now. That's it. It's easy enough to remember and follow on a diagram. Okay, work out, think about this now for a few seconds, couple of minutes. Is there a deadlock here? Oh, sorry. Is there a deadlock here? Yes or no? So I try to terminate, remove all the links. Would you be able to move all the links? What's this called? What's this called? Is this a process?
It's a resource.
What kind of a resource? That's a resource there. 3 or 4. This is not just an ordinary resource. Yeah? Yeah, this is a multiple instance of a resource. Like we have 2 items, they are identical the same. See, it depends on how many dots in there. Let's say these are printers. If this is a black and white printer and that's a color printer, they would not be identical here. They can't be an instance of the same resource unless they're exactly the same. And it doesn't make any difference to a user whether they get this one or that one. Then they're called instances of the same resource. So we have 3 of them here. You can satisfy 3 users at the same time. Like this one here. Now, one is allocated to process 2 and one is allocated to process 1. So is there a deadlock here?
No.
No or yes?
No.
Okay, where's the deadlock? Who's saying there's a deadlock? Okay. No, speak for yourself. I think Aisha is not really supporting you there. Resource 1. Okay, what about it? R1 is going to, pointing at process 2. That means it's allocated to process 2. Process 2, does process 2 have everything it needs? It needs 3 resources. Does it have them? No, it has resource 1 and resource 2, but it needs resource 3. It doesn't have it. So, go on. Process 3, can we terminate process 3? Yes, it has everything it needs. There's only one, it needs 1 resource and it has it. It's actually allocated to it. So, the first one we get rid of is process 3. So we can remove this link and we say process 3 has finished with resource 3. So what are we going to do with resource 3? Allocate it now to process 2. So this link will turn around and go towards 2, and number 2 now is finished, it has everything it needs. It has resource 1 already, resource 2, and now we're going to give it resource 3. That means it has everything it needs, which means it will finish. And when it will finish, it will release resource 3, it will release resource 1 and resource 2. Who needs resource 1? Process 1 needs it. Let's give it to it. And now process 1 has everything it needs, and it will finish, and it will release. So all the links are gone. There's no deadlock. All right, so this goes this. All right. So there it is. Oh, I have it. I forgot I had it done. I think. All right, so the first link that will go is this link, because process 3 will finish. So the link will go. And then what do we do with that resource? We should allocate it to process number 2. So now process number 2 has all the resources. It needs 3 resources and they're all allocated to it, pointing at it. And that means it will finish and will release them. Now, resource number 1 is free. We can give it to process 1. There. And finally, process 1 has everything it needs. When it needs, it will finish. And when it finishes, it will release both resources. And then all links are gone. There's no deadlock. Okay, that's the way to do it. Is that clear? Good. Can you work this out? Okay, let's go for this one first. Hold on. Is this the same one? Yeah, sorry, okay. Whew. Let me go to another one. Go to this one. Right. Work this out. Remember, in an exam, you'll write those statements that I've been saying. This one is allocated to this one. It has everything it needs. It will finish. It will release those links. This link will be allocated to this process and in the same sequence. Okay. Is this how I did one? Yes. Everything is released. All links are released. Okay, start with the top process. Process 2. You start with any process that has everything it needs. It's already allocated. Process 2 has resource 1 now. Resource 1 is allocated to process 2. Doesn't need anything else. That means it has everything it needs. What does that mean? It will terminate, it will finish. And when it finishes, what does it do with the resource it has? It will free it or release it. So resource 1 will be free. Anybody looking for it? Yeah, process 1 needs that. So we'll allocate it to P1. And see if you can release everything before links are released. Is there a deadlock? Haven't checked it yet. Come on, start with one. Start either with the very top process or the very bottom process. So it only needs one resource. See, there's process 1. Point to resource 1 that's going to process 2. So resource 2, the other resource in a second. See, that resource 1 has 2 items. Process 2 already has 1. The 2 resources are already allocated. The top one.
No way.
Okay, guys, I don't know if you've finished or reached a conclusion here. Is there a deadlock or not? Did somebody say yes? Okay, let me go through this. I don't know if I have it marked. No, unfortunately. Okay, this is the way it goes here. Always look for a process that has everything it needs. Camus. Okay, so in this diagram I can see two processes that have everything they need. Process 2 and process 4. Process 2 here needs one resource, and the resource is actually pointing at it. That means it already has it. It's allocated to it. For example, it needs a printer and it has it. Remember, resource 1 has two instances. That means there are two similar printers sitting there. One of them is given to process 2, is allocated to process 2. So the way I'd see it, I'd say an instance of resource 1 is allocated to process 2. Process 2 has everything it needs. Once a process has everything it needs, you can immediately say it will finish. It might finish in 1 second, might finish in a minute, it doesn't matter. It will finish. It's like, I don't know, if you're hungry and there's food there, just a matter of time before you devour that food and then you're no longer hungry. So we assume you're okay, you're fed. So same with process 2. It only needs one resource and it has it. It will finish. And when it finishes, it will release that resource. So this resource now, the top one is free. This one device here is free. Anybody looking for that? Yeah. Process 1 is looking for that. Can we give it to process 1? Yeah. So when this is released, now we give it to process 1. Does that make any difference to process 1? Yeah. If process 1 gets that, as well as the one that it already has, remember process 1 is pointing to resource 1. I need that. It's requesting that. Now we give it, we reverse that arrow. So now process 1 has 2 resources. That's all it needs. It has the 2 of them, so it will finish. And when it will finish, it will release those resources. So this link will go, and this link will go. So now this one, R2 is free. What are we going to do with it? We can give it to process 3. Process 3 now has the 2 resources it needs. It will also finish, and when it finishes, it will release those links or those resources. We can remove the link. And this one, process 4 also, we could have finished it first one as well. It only needs one resource, and it already has it allocated to it. So this system has no deadlock. When we can clear all the links, all the processes will finish without a deadlock. Is there a deadlock in this system? Follow the same rules. Start with the process that has everything it needs. If not, can we give it a free resource? If it needs 2 resources, one is available and one is free, give it the one if it will finish. We can say, first thing, let's allocate this to that process. Okay, think of this. Where would you start in this? Where would you start? What would be a good starting point here? Is there any process that has everything? No. No. Okay, this process, it has this resource but needs that one. Is that free? No, it's not. Well, then it cannot finish. Let's go to process 2. It needs 3 resources. It has this and this. It needs that resource. That's not available either. That one is allocated to process 3. What about process 3? Can it finish? It needs 2 resources. It has this one and it needs that one. Is that one available? Nobody's going to finish in this. There you go. That means there is a deadlock. Now you have to find out what's the sequence of deadlock. The sequence is pick one point and go trouble, and if you come back to the same point, that's the sequence. Just give me the list of those processes and resources you pass through. For example, if I start at process 1, I can go to resource 1. Let me start with process 1. I go to resource 1, bring me to process 2. Can I go back this way? No, it can't. It can't follow this arrow. It's in the opposite direction. So we can't go back to process 1. But maybe you can do this way. Process 1, resource 1, process 2, process 3, or resource 3, process 3. Go to resource 2 and back to process 1. We get to the same point. That's a deadlock sequence. So the deadlock sequence is something like this. You need to write them. P1, R1, P2, R3, P3, R2, P1. Bring you back to the same point. These are the processes that are deadlocked. Process 1, 2, and 3, they're all deadlocked.
Are there two sequences of the deadlock?
They could be. There could be two sequences. There may be another sequence here. Look at this one. You can go P2, R3, P3, R2. The arrow brings us back to P2. So yeah, in fact, in this system, it's so complex, it has two deadlock cycles or sequences. Is there, yeah, sorry, yeah?
Didn't mark the attendance now?
Att-
Didn't mark the attendance.
I'm not going to take the second attendance, it takes too long to do, so I'm going to ask them I'll tell them it takes too long, and just consider everybody who was in the first. Count them that they're in, or don't count that at all. Doesn't go into the system. Okay, is that good enough? It's going to take too long. It took too long for us to register the first one. Right, is there a deadlock here? Come on, guys. Easy enough to follow. Is there a deadlock? No. Sure? Okay, guys. This is the way I start this one. Okay, this is the second last diagram. Alright, I look at process 1. Does it have everything? It has resource 1, but it needs resource 2. Can we give it? No, they're all busy. So leave it. Look at process 2. Does it have everything? It has resource 2, but it points at resource 1, say I want that. And it's not free, then it will not finish. What about process 3? Process 3, it only needs one resource, and it has it. It's already allocated to it. So it doesn't need anything else. That means it will finish. Let's jump into the future, 2 seconds or 2 minutes in the future, it's finished. It will release this one. So now this is free. Who's looking for resource 2? This one, process 2? No, process 2 already has it. This one is looking for it. Process 1 is pointing at this resource, say, I want that. Yeah, we can say, you can have this. So we give this instance of resource 2, we give it to process 1. Now process 1 has 2 resources. It has resource 1 and it has this now, so it doesn't need anything else. What does that mean? It will finish. When it finishes, it will release this and that. Anybody looking for resource 1? Yeah, process 2 is looking for it. We reverse the arrow, we give it to process 2, it will finish. And they all finish, and there's no deadlock. Okay, have a look at this one. If you do it, you finish it, you can go home. If you don't finish it, you stay here. Start with the process that has everything. Probably there's no, I can see one already, very quickly. There's one process, it only needs one resource and it has it. Which one is that? 3? 3, no, 3 needs 2 resources. It has one and it needs this one. This one is not 3. 5, it only needs 1 resource. And it's not asking for it, it already has it. See, think of the arrow, if it's pointing to the process, that means this resource is now with this process. Think of the process as a person. Either points at something and say, I want that, or it already has it. So process 5 will finish, and to release this, anybody's looking for this? Process 3. Oh yeah, you meant process 3 arrow. Yeah. Now we can give this to process 3. 3 now will finish. It has everything. It will release this one and that one. That one now can be used by number 2. Pardon? Number 2 will finish because we can give it this one. And it will release this one that we can then allocate to 1. 1 will finish, will release that one. In fact, process number 4 could have finished earlier. Yeah, that's another one, good one. But it's, it's a bit more complex than just a simple one, just with 1. But yeah, process number 4, we could have given it this one right at the start. It already has this and that. And we could have given it one of the instances that's resource 3. So process 4 will finish. We'll release this one that can be used by 3, maybe, or that's it, or this one that can be finished used by 1. So there are many ways to finish this, and there's no deadlock. But you need to write those words. Who finished? Who needs this? Which one is allocated? Which one has everything? Which one is releasing what resources? So this is on Moodle. Have a look at it. There will be a tutorial, guys. Don't tell me you didn't see it. I don't know when I'm going to put the tutorial on. Maybe this weekend, maybe tomorrow. Please, don't waste any more those who missed the tutorial last time. Good luck and have a good weekend. And I'll see you next week.